with simulation and reinforcement learning. So I'll let Tom explain his work a little bit more. Tom, thanks for joining us.
Thanks for having me. I wonder, do you guys both see me and my screen, or only my screen?
Only your screen.
Okay, so that means I can do funny faces.
Perfect.
All right, good to know. So thanks for having me. It's a bit odd for me to meet all you wonderful people in such a virtual setting where I can't feel the room and I can't gauge for engagement and background knowledge and all the nodding of the heads and all of that. So I will try to invite you guys to occasionally chat into the main chat room, maybe just one character occasionally as a proxy of a poll, just to see that we're all on the same page. So I will go for a non-conventional structure for this presentation. I will start with the non-technical part, the polemic part, and I will make some less grounded arguments about deep learning and robotics. And that will hopefully motivate the technical part, which is digging down into rigid body physics simulation, which is my technical expertise. So I will invite plenty of pushback during this polemic section, and definitely at the end we can dig into it as much as you want. So first of all, who am I? I did my undergrad in maths, and then I did my doctoral work in computer science. I did a postdoc with Amo Todorov in University of Washington in Seattle, working on the physics engine MuJoCo, and I joined DeepMind as a research scientist in 2014. DeepMind is effectively a research institute. It's funded by Google, and currently it has about 1,000 people, most of them in London. DeepMind's motto is, we want to solve artificial general intelligence and use it to make the world a better place. And I consider robotics to be key to both parts, both because I consider motor intelligence to be a critical part of artificial general intelligence, and I think we would need robotics in order to make the world a better place. So let me go right to the more polemic part, deep learning and robotics. So let's start with a caricature, a cartoon of the standard run-of-the-mill robotics workflow pipeline. First of all, you're given a challenge and you're trying to understand what are the problems there. Then you would probably decide to use some representation, and you will come up with that representation using your intuition or experience or the best practices from your teachers or whatever. And that representation will be that computational space in which we're going to, quote unquote, solve the problem. And then, because at the end of the day, there's a real robot in the real world, you will need to gather observations and output actions. So you would probably want an estimator that would map from observations into that state space. And you would want some policy that would map, or controller that will map from this state to the actions. And both of them can have multiple stages, and that would probably mean that you will craft some intermediate representations for every subcomponent. Then, very importantly, you need to convince yourself and the owner of the robot that this setup is not going to break the machine. And then you can try it out. And after you try it out, you refine the various components in the pipeline. I am curious, with a quick vote in the chat, to how many people this sounds self-evident, and to how many people this sounds a bizarre way to think of things. So type B if you think it's bizarre, and type O if you think it's obvious. All right, I do see a few B's. I see many O's. I admit that this is a caricature, and at the many robotics projects in practice will have all sorts of shapes. I do want to defend this view in two ways. One is the key point that I'm making is that as roboticists, we craft representations. The biggest advances in robotics, the best paper awards go for new representations. When we came up with zero moment point, we solved a legged locomotion, and Boston Dynamics came to being. When we came up with a signed distance function, we solved a dense volumetric estimation, and Kinect Fusion got the best paper award. When we came up with the representation of the quaternion, we got over the gimbal lock. So this is what I mean by representations. Further, I would claim that this component-based approach is necessary for a mature field, because we cannot get every robot to be born out of nothing. So we need off-the-shelf components, and these components have to decide on some API to talk to each other. So there will be these representations that will communicate between the different components. This is not an indictment. This is merely a description. However, what are the pitfalls with this kind of a chaining approach? First of all, this chain of components is only as good as the weakest link, because if one component breaks in the chain between the photons hitting the camera sensor to voltages outputting to the motor, any link in this chain fails and the robot no longer does what it needs to do. And as soon as you chain components, you introduce secondary effects. And those effects usually decrease performance. So I am curious to hear, again, in a poll, especially those who thought that the previous description was bizarre, are you still feeling that I am that my description is an abomination to the art of robotics? Type A if you think it's an abomination. I will take this silence as a cue to continue. All right. So in order to understand what deep learning can do for us in robotics, let's take a cue from machine vision. So in the old days of machine vision, before machine learning came into play, David Marr in the 80s and stuff like that, the machine vision researcher would design a feature, and that feature would describe a space. And that representation, that space of features, you would then build a classifier or detector in that space. You would detect lines, and then you would try to classify for a square or something like that using rules of geometry. As machine learning and statistical methods came into play for machine vision, we switched modes. We were still designing features, but we were using statistical methods to learn the classifiers from the data over the space created by our crafted representations. And then the deep learning revolution happened. So if you look at 2010, perhaps it's a bit hard to see, but we were crafting representations with a dense grid descriptor. And then we were coding these descriptors with some coordinates and vectors. We did some pooling, and we did a thin layer of statistical machine learning on top, a linear SVM, and that was the best thing that happened in CVPR in 2011. Actually, the best paper award in CVPR 2011 was the Kinect. If you guys remember that gaming console from Microsoft, the way it used depth images to infer the pose of the human in front of the Kinect cameras was the best paper award in CVPR 2011. But then deep learning happened, and people were suddenly presenting architectures that looked ever deeper and ever more bizarre, mapping from pixels to labels. And what's weird is that those models were that much better. Now, to understand why this is so weird, let's go back to basic statistics. There's a trade-off. Statistics people tell us there's a trade-off between bias and variance. And if you are using a model that underfits the data, you will have a lot of bias. And if you're using a model that overfits the data, you will necessarily have a lot of variance. And you're looking for some optimum between underfitting and overfitting. And the traditional view in statistics and machine learning often describes something like that. As your model becomes more complex, your bias will decrease, but your variance will increase. And therefore, there's a sweet spot right in the middle of the model complexity, not too complex and not too simple. Before I switch to the next slide, I want to take another quick poll. This bit about bias and variance, is this obvious or bizarre? I want to see people typing. All right, capital O, great. I'm going to roll with that. All right, and then people came and presented papers that were using this kind of architecture, which has been studied since at least the 70s. And these kinds of architectures would take the input and would iterate through multiple layers of this simple and semantically almost meaningless computation of applying some linear transformation and then applying some nonlinear transformation, and then at the end of the day trying to get a label out. And there's nothing in the statistics and machine learning literature that would tell you that this is any better than SVM or anything else. But to everyone's surprise, the models became more and more complex, and the success of the models became better and better. And this is a paradox as far as the classical view of statistics and machine learning is concerned. Deep learning is unreasonably good at learning and generalizing. And this is like, I would argue that we are still in the pre-Copernican phase of understanding deep learning. We're still just collecting random observations about how good it is, and we don't yet have a view, an organizing theory to understand why it is so good. But I will try to give you some of the intuition that I have, at least. The thing that happens when you train a deep architecture is the emergence of features across different scales. So if we're training a classifier for cars and we allow it to look at many images of cars, the low-level features are going to look like Gabor filters or color splashes, which is similar to what we see when we record close to the retina. And it's similar to the kind of SIFT models that were state-of-the-art in the end of the first decade of the century before deep learning started. So we knew that we have good reason to believe that this is really a good low-level representation. And then if you probe these mid-levels in these deep hierarchies, you see these funky features that detect a corner or a circle or a curved line. And as you move closer to the output, you find features that are semantically closely tied to the label. You see a beak of a bird. You see a hoof of a horse. You see the wheel of a car. You start to see the kind of cues that are clearly relevant for the label, for that output of the model. So this kind of natural emergence of hierarchy of features is the wind under the wings of success for deep learning. And it allows us to do all sorts of really bizarre things. Like we can take just the low-level features of a Van Gogh painting and apply it to some random image and get something that looks like Van Gogh, because locally every 50 pixels look like Van Gogh, but the picture as a whole, the high-level features, look like a dog or a cat. So this should give you an intuition, at least a vague intuition, on the difference between the high-level features and the low-level features in these images. And the magic in machine vision happens because they dumped the crafted representations and they committed to end-to-end learning. And in machine vision, this is a very obvious interpretation. You start with the pixels and you end with the labels, and you don't stop anywhere in the middle. And the amazing lesson is that learned representations are better than crafted representations. No one crafts representations anymore in machine vision. Now, instead of designing these representations and intermediate components, the researcher still has a lot of work to do. But the work has the form of curating the data set, deciding on training losses and auxiliary losses, doing data augmentation. There's still a lot of artistry, or a good researcher would still get better results than a bad researcher. But this no longer has to do with crafting a better representation. Now, the challenge that we need to remember if we try to carry this lesson over to robotics is that it's impossible to provide performance guarantees in the way that control theory often demands. And the reason control theory is offering us guarantees is not because our professors are pedantic, but because we're trying to get to the moon and we are trying to use multiple vendors and multiple components. And if we are not going to get guarantees for each component individually, we won't trust that airplane, we won't trust that spaceship to get to the moon. So control theory has a good reason to be pedantic. Similarly, reuse of components from deep learning is not a given. That example that I showed about the Van Gogh paintings is the result of someone working really hard. It is not obvious to us yet how to mix and match components of deep learning. So where is machine learning and deep learning in robotics these days? In practice, if you look at the occurrences of deep learning in robotics papers these days, it's usually applying deep learning to individual components in the pipeline. We're going to learn a detector that will go from pixels to quaternions. We're going to learn a detector that goes from signed value functions to object label. And then someone else will take the responsibility of going from object label to actions, or from pixels to signed distance functions, or something like that. Now, in the academic world, people are excited to explore end-to-end reinforcement learning. And here, end-to-end really means going from observations to actions. And there's people are trying all sorts of additional methods on top of that, if it's meta learning or imitation learning or transfer learning and other ideas. And there's so much to cover there, and we're not going to cover it today. But the ultimate goal is important for me to communicate. We are trying to dig deep into intelligent motor behavior. We're trying to solve robotics from the deep end. We are trying to get to a situation where our robots will take the observations that are given to them and will choose the right actions to perform intelligent behavior. And this is necessarily embodied intelligence, because it is necessarily a sequence of decisions over time with high dependence. This is not some application of arbitrary labels to pixels. So this is a much harder problem than merely machine vision. So let me just remind myself where the flow is from here. Okay, I'm going to talk a little bit about reinforcement learning. Before I go to reinforcement learning and deep reinforcement learning, I want to take a moment and give people an opportunity to ask a question. Just unmute yourself and voice your concerns to the air. Okay.
Sorry.
Please go ahead.
I'll also add that if you're not comfortable unmuting yourself, and you're welcome to also ask questions in the chat as well. So.
Please, yeah, of course. Type your question. You can even chat your question to me personally, not to everyone if you want.
I had a question. So Tom, are you saying, can you hear me?
Excuse me?
Can you hear me, by the way?
Yeah, we can hear you.
So are you suggesting that end-to-end architectures would be the best way to control?
That's a good question. I think the ultimately intelligence is measured in the end-to-end context. At the end of the day, you put the robot in the room and it takes in observations and it outputs actions, and it's either smart or not. Can we realistically hope to go from voltage spikes in the image sensor all the way to voltages outputs in the motors and everything will just work? Probably not yet. And therefore, we will necessarily need some compartmentalization and some, onboard controller and some basic image processing. And we are necessarily diminishing the end-to-end aspect, and we are bounding our success. We're only as good as the onboard controller. So I think robotics is a rich field, and even if you're not doing machine learning and reinforcement learning, you can still contribute to the state of the art. We definitely need people who know why this communication bus is laggy. But I think of intelligence as the more abstract question. In particular, and that is the most polemic statement I want to make later in this presentation, I think we can probe the question of intelligence purely in simulation and sidestep all of those very hard technical questions that are only tackled on a real robot.
Okay.
Does that answer your question?
Yeah, more or less, yeah.
All right.
Come back to it later.
Yeah, that would be great. All right, so let's quickly run through reinforcement learning and then maybe talk about some simulations. So the basic paradigm of reinforcement learning is an end-to-end approach to behavior. There's an environment, and this environment is here represented by a robotic arm next to a tree. And the environment provides some observations in blue. And the observations are the input to the agent, which happens to be a deep neural network architecture. And the output of that computation is an action. The action affects the world. The world has a state that is unknown to the agent, but now the state has changed and the observations have changed. And the agent maybe has also its own state of mind, and its state has changed and new actions are outputted, and that is the basic loop of behavior. There's also a reward signal that's coming to the agent from the environment, and the better agent yields more cumulative reward. It's as simple as that. So historically, in DeepMind, we started by looking at games like Atari, and in the beginning, the agent was really not good at it. And then a few games later, as more experience was gathered and the mapping from observations to actions became clearer, the agent started doing things like this. And then, unexpectedly, the agent discovered a new trick, which is this, which is the holy grail of the breakout game. And we were proud of ourselves in DeepMind, and then we designed harder benchmarks that are more relevant for robotics. So here the agent needs to apply torques to the joints and throw itself over ever-widening gaps. And other successes. Can you hear the video? If you can't, chat to me.
We use reinforcement learning and simulation to teach the robot how to solve tasks in the real world. To learn how to solve a task like this, we show it many different variations of the world, where the rules are slightly different every time. This is a technique called domain randomization, and it affects, for example, the color of the cube and of the background. However, we take this technique beyond just how the environment looks. We also randomize aspects like how fast the hand can move, how heavy the block is, and the friction between the block and the hand. Our learning algorithm sees all of these different worlds, and this lets it learn a way of manipulating the block that's very robust. Robust enough so that eventually...
All right, so this is a project from OpenAI from 2018 using the very complex robot called the Shadow Hand, manufactured in Islington, London. And they created dexterous motor behavior that was really impressive in terms of setting a new state of the art. And they did it by learning in simulation and transferring to the real robot. And in order to get a robust controller, a robust policy learned in simulation and transferable to the robot in a zero-shot manner, they processed, I don't remember, maybe 20,000 years of simulation data, something of that magnitude. So the Shadow Hand, there's a company called Shadow Robotics, to answer the question in the chat. And this is really the state of the art in hand manipulation of in dexterity, and it's an impressive result. But let's think about the limitations that are exposed here. First of all, the task design. How do we initialize the task? What is exactly the reward that we're giving? Is it about quaternions, or is it about Cartesian distances, or about what? When do we terminate the episode? The task design is an art. So we are no longer designing a policy, but we are still designing something. And it's still tricky to design it. And furthermore, the state-of-the-art reinforcement learning, the data complexity is absolutely prohibitive for learning on a real robot from scratch. We don't yet know how to do reinforcement learning that efficiently. And that is why I think rigid body simulation is a critical component for robotics research, because robotics research is about embodied intelligence research, and embodied intelligence research right now requires more data than you can gather on a real robot. That is the center point of my argument. And with that, I'm going to transition and talk about rigid body simulations. So before I go to a more technical part, I want to see if there are any questions here in the middle of the narrative arc. You feel free to chat your question. All right. So where is rigid body simulation in the overall map of simulations? This slide could have a lot more graphics and they could be really exciting, but try to use your intuition and background to fill in the gaps for me. So if we look at the axis of complexity, the simplest RL problems historically have been problems of grid world. You can move in X and Y, or maybe even in one dimension, and there's some goal somewhere and you need to get there. And people have spent decades studying questions of behavior in grid worlds. And then if you think of something slightly more interesting, you think about games like Pong or Breakout, where there is some basic notion of physics. That dot moving on the screen does resonate with some intuitions we have about collision and maintaining of velocity and momentum. Going slightly more complicated, you can think of 2D mazes like Montezuma's Revenge, where you move in the screen and you can jump up and down and certain things can fall and kill you. Even more complex would be a world where you move in 2 dimensions and you look at 3 dimensions. And this is a first-person shooter or a first-person navigation game or something like that. So the visual scene is now really complex and interesting, but the physics is still really dumb. Everything are just planes that you either go through or you don't go through them, and that's it. And you're basically a sphere in a world full of boxes. Going slightly more complex, we can think about rigid body physics. So objects are still perfectly rigid, but they can have all sorts of shapes, and you can pick things up, and you can throw things around, and you can smush things into each other, and you can fit puzzle pieces together, and you can do all sorts of interesting effects with friction and normal forces. If we want to go beyond that, we have to move to more complex methods like the finite element methods. Maybe in 1 dimension and things only bend or only compress along that 1 dimension. Or maybe you want to do volumetric finite element methods and you're really simulating the touch pads, the gel touch pads at the end of your robot finger and how they compress when they touch an object. Or maybe you really care about multiphysics and the way heat transfers as you move, and because you press now, the cold object chills the inside of your motor that's close to the finger pad or something like that. So we can simulate all sorts of effects. And I am proposing a very tentative suggestion, and I can totally see someone pushing back on that. But I'm going to propose that there's a law of diminishing returns from the perspective of thinking about intelligent behavior. As we went from a grid world to first-person navigation, we really opened up the table. We opened up the opportunity to ask much richer questions about the understanding of the agent of the world around it. And definitely we added more when we are simulating the full rigid body physics. But as we add more and more details and fidelity to our simulation, we are spending more flops, really, teraflops, if we're doing the whole multiphysics thing. And what do we gain in terms of being able to ask questions of intelligence? I claim, and again, this is my personal view, that rigid body physics is the sweet spot in this bang for the buck, in flops for the insight onto intelligence. And that decision guides my research agenda and my technological agenda. So I'm just curious, before we dive into the details of rigid body simulation, I'm curious how many people are on board with that claim that there are diminishing returns and that rigid body physics is the sweet spot for the investigation of intelligence. I want to see a yes or no, whether this jives with people's intuition or not. So just type Y or N, and let's see where everyone stands. All right, we saw many yeses, a few no's, and a few people who don't know yet. And let's say that I'll give you some technical details just so that we have some equations to sink our teeth into, but I will gladly talk more about these questions on the other side of this technical bit. I feel like they're interesting discussion to be had about this rather abstract point that I'm making. So, in general, this is true for any physical phenomenon that you want to simulate. There's a trade-off between speed, accuracy, and stability. You can always have two of them for free, but you can never have the three of them. If we want to simulate a robot arm on a table, if I want to simulate something that's really fast and really stable, it's not going to be accurate. The robot arm will either go through objects or it will not be able to get close enough or something like that. And it can be really fast and really accurate, but we're going to have numerical divergence everywhere, and it's going to be impossible to use. And we can have something that's really stable and really accurate, but it's going to be really slow to compute. So that's a trade-off that this is true for any simulation project. Now, I'll tell the story of rigid body physics in 3 chapters. The first chapter is about what I call smooth dynamics. So this is one of 2 slides with equations. Bear with me. Newton tells us that F equals ma. And if we have multiple objects, both F and A are vectors, and therefore M is a matrix. If we're going to go with the Newtonian framework, we have position, velocity, and acceleration. And we're going to split the state space X into position and velocity. And their time derivative is the velocity and acceleration. And so we have this m to the minus 1 times F. And as long as we don't have constraints, this is the equation that we need to solve. But even this equation is not easy to solve when we have joints. So merely introducing a kinematic chain with joints is going to be require some math. If we talk about a body, it's just a frame in space and it has 6 degrees of freedom. It can move in x, y, z, and it can rotate about x, y, and or z. If I connect 2 bodies with a joint, the effective number of degrees of freedom is not 6 plus 6, it's less. I'm going to say that the joint requires that these points in body A must be exactly at these points of body B. And for example, a hinge, a revolute joint, will leave only 1 degree of freedom. So it removes 5 degrees of freedom. So for example, think about scissors. How many degrees of freedom does scissors have? You take a scissors and you can move them in space in all 6 directions, and you can open and close, and that's the 7th degree of freedom. And now it's a question of a representation. We are crafting a representation. How should we represent these degrees of freedom, and how should we represent the joints? And in the game industry-driven physics engines like PhysX 3 and Bullet 2.7, you would represent the body as 6 numbers. And joints would be constraints. So introduce constraints to the equation. Now the numerical solver has to somehow change those numbers to satisfy the constraints. That makes it simple to define your model, but perhaps very hard to solve. And indeed, when people tried to do the computation that will power the arm on the space shuttle, the dynamics, the joint dynamics of that arm was just too important to leave to some constraint resolution numerical tricks. And so scientists in NASA developed new mathematical tricks to compute joints in a minimal representation, as opposed to the maximal representation that is common in games. Now, the root of your articulation, your system of joints, has 6 numbers, but now every joint adds degrees of freedom as opposed to removing them. So a hinge will add 1 number, and a spherical joint will add 3 numbers. It can rotate in every direction, but that tip has to be right where it is connected to its parent. The computation is more involved because you have to figure out in what ways things can and can't move. Articulated joints will never break because by definition you cannot express a pose where the 2 things that are connected in the joint are far from each other. Your upper arm and lower arm will always be connected at the elbow. But the simulation may still diverge. This is the numerical challenge is still present. So just to entertain you, if this is a humanoid model, the mass matrix of the maximal representation is just a diagonal. Every body is independent, and it's the constraint resolution's job to bring the upper arm, the lower arm together. In a minimal representation, the mass matrix becomes something non-obvious. The mass matrix describes how one limb depends on another limb. So it has a very particular structure of sparsity. Just to entertain you, what does divergence look like? Divergence can happen, and this is a numerical fact that affects all interesting simulations. So once we figure out how to do joints, what we really care about is not merely bodies moving in free space, but affecting change in the world through friction and through contact. And so we need to account for the computations that involve contacts. So if any 2 colliders or geoms or some volumetric representation, if they overlap in 3D space, that's illegal. And we need to apply some forces to push them away from each other. But you can't continue applying those forces if they no longer touch each other, right? So now the physics engine's job is to figure out who touches whom, figure out what is the right direction of the normal force, how do we push them apart, and then figure out how much normal force to apply, which way it should be directed, and how much we should apply. So it's important to note that convexity is necessary. If we have a concave shape, I have no idea which way is out. How do I push that black object so that the overlap is reduced? This will frustrate any numerical algorithm to no end. If the shapes are convex, however, we can identify some point and some direction that is guaranteed to decrease the overlap. And it is guaranteed that if you push long enough, you will detach. And that would be a good time to stop applying that force. So how do we do collision detection? This is, in general, you can look at every two geoms in the scene, every two colliders, but that's numerically prohibitive. So you first do a broad phase and you try to prune your tree, who is definitely not touching each other. And then you do a narrow phase and you ask exactly who overlaps with whom and where, what is the normal direction, which way is out, and how is that direction relating, how does that relate to the degrees of freedom of your system? In a maximal representation, it is trivial. I want to move that way. In a minimal representation, this is tricky. If I want to move that way, what do my joints need to do? That would be the contact Jacobian, the derivative of the penetration with respect to the joints. This is not trivial to compute. If we have primitive shapes like a sphere, we have some closed form equations on how to find the normal force. If we have meshes and more arbitrary representations, we need to use a numerical solution, some algorithms that will traverse the triangles of the mesh to find the way out. And finally, we need to find the forces. So if you remember, we had Newton, F equals ma. But now we're going to say subject to some constraint, some function S that has to be greater or equal to 0. And as you may have seen in some classes in university, the way to solve, one way to solve constraint equations is with Lagrange multipliers. So we're going to find some multipliers that will apply to the Jacobian of the constraint function. So these multipliers are effectively forces. These are contact forces. And the Jacobian of the function S maps from contact forces to joints. So if you push on my finger, these are the forces I will feel in my joints. And together with the torques that I'm applying at my joints, this is going to be the resulting acceleration. So you clearly see how, as we formulate the numerical problem, we can use standard computation tools to solve for the Lagrange multipliers, and we will get contact forces as a result. So how do you compute that? It's too hard to talk about. You need to balance, as I said, accuracy, stability, and speed, and different constraints toggle on and off as you move. You can use off-the-shelf algorithms, Gauss-Seidel, quasi-Newton, whatever. There are interesting counterexamples. This is not a well-formulated problem. So there's a lot of artistry there, but usually we are just clients of those numerical packages. This is the job of the physics engineer designer to get this right for us. And yeah, as I was saying earlier, a rigid body simulation will not solve robotics because there will be unmodeled physical effects like bending, joint slack, thermal effects, and whatnot, and the question of system integration. But polemically, I claim that we will not solve robotics without artificial general intelligence. So I have some design consequences. If this is what rigid body computation looks like, you should try to avoid effects like tunneling, and you can encounter things like jamming. So if one segment tunneled and another segment didn't tunnel, you have this case of the poor conductor whose head got through the door. Let's look at that again. This is from some game. I'm not even sure which game. So his head got jammed in the door. And then the script of the game takes over and saves him. And you get these weird effects when you try to do convex decomposition of meshes. And at the interface between two parts of your decomposition, you can get really weird effects. Maybe as your finger moves across the surface, you're feeling a bump, or maybe you're feeling a notch. And these effects can be very meaningful for the behavior of the agent. The agent can learn to abuse these effects and jam things into the crack in its knuckle. So this is the art of my trade. And that's a good place for me to stop and stop sharing my screen and instead put the camera back on and start the more open-ended part of this conversation.
Okay.
On my screen, my video is frozen. Are you guys seeing me well?
I can't see anything. Oh, there you go.
Perfect.
Yeah, now it's
Okay. Yeah. So ask me anything from conservation of momentum to artificial consciousness.
maybe I can start. So when you're actually simulating something, isn't that going against the end-to-end architecture? Because in some way you are doing some low-level representation, right?
That's very true. I am only as good as the representations that I chose for my simulator. And that's why I am labeling my assertion as a polemic one, that rigid body physics is rich enough to tackle deep questions of intelligent motor behavior and fast enough to compute efficiently and give answers within our lifetime, as opposed to volumetric finite element methods. In light of the current constraints on data complexity of the algorithms that are currently state of the art. If someone came up with algorithms that are that much more data efficient, then you can start using better simulators, then you can start using robots. Just learn on the robot from scratch. The reason I am not tremendously optimistic on the prospect of that is the fact that the existence proof of motor intelligence is a squirrel or an ape or human, and this is the fruit of hundreds of millions of years of evolution and many months and years of practice. And maybe we will be able to eventually encapsulate all that knowledge as a good starting point, and with that knowledge in place, go and do a successful project on the robot. But I think right now, in the current computational and engineering landscape, the best way to tackle these questions is with rigid body physics simulations.
Right.
So what are your thoughts on sim to real and the importance of that as a research question? Or do you think it's better to purely utilize simulation to explore these questions about intelligence and then kind of worry about that later down the line once we have the compute power available to kind of explore that and actually take these approaches into the real world?
So it's a question of taste and funding opportunities. If you, like, it is often the case in our world that if you're not going to show something cool on a robot, within a year or two, they're going to pull your funding. And then you better find a way to show to the rest of the robotics community that what you're doing is actually relevant on a real robot. I personally have the privilege of working in a research institute that values AGI above all else. And I can afford to lean back and ask what is often a very theoretical question, because a simulation is, as we said, it's a theory. Now, sim to real holds a promise. It held a promise in theory for many years, and now it has delivered the state of the art in certain otherwise impossible benchmarks. So I think sim to real is a great avenue for yielding impressive results on robots. Unfortunately, it's an art. It took dozens of engineers in OpenAI for multiple years hacking on that problem until they got the right distribution of simulation parameters to where the controllers started to transfer well. And they had to go back and forth between the real robot and the simulation. They added certain features to the robot to make it more simulatable, and they added features to the simulation to make it more robot relevant. So I think sim to real is a great problem, but I think even if you are not taking that approach, there are very interesting questions to ask. Did I answer your question?
Yes, thank you. That was really interesting. Oh, sorry, just one follow-up. I think robots, at the end of the day, we want to make useful robots that can solve problems, especially at the moment in all the challenges we've got in the world with environmental issues, COVID, etc. Is there something about actually kind of focusing on actually making robots to solve problems? And should we position more of our efforts actually into solving practical problems? Or how do you see focusing on simulation now as a way of then being ahead of the game and progressing with the tools we have available? And then that's a more efficient way of solving these big problems than actually kind of messing around with robotic hardware and getting stuck with the physical limitations of current technologies.
This is a question that can be asked in almost any discipline. In every research field has a Pareto curve where you balance immediate relevance and long-term contribution. And asking questions about abstract behavior in simulation and playing video games is not going to make testing faster, COVID testing faster. It's not going to move the test tubes in the lab faster. So it is between the researcher and their conscious and their funding body to decide what is the right balance to strike. I will say, though, that if you, as a PhD student who got funding and got to do whatever they wanted, I enjoyed playing those video games, and I felt that I'm asking deep questions. And as a member of a research institute that is not doesn't have to deliver robotics applications to pay for the next year of operation, I again enjoy asking questions in simulation. But clearly, I don't want to see the whole robotics world dropping their screwdrivers and going to the computer screen and playing video games. So I see a question in the chat. What is the usual practice in translating a real-world robot into rigid body simulation while ensuring accurate representation of the original robot? Great question. This is called system identification, and it is an art in its own right. It's an art for, maybe you can get some of the way by reading the CAD models of the robot, and at least you'll get some of the kinematics right. And then you need to think about how are you going to wiggle the arm and what are you going to measure. Maybe you're going to wiggle it once and then you wiggle it again with some mass at the end. And maybe you're going to measure the proportion between position and velocity, or maybe between velocity and voltages, or any other measurement, and you're going to try and fit that and not some other quantity from your simulation. So there are papers on system identification. It is its own world. To the extent that you want to do sim to real, or you want results that will be directly relevant to some specific robotic platform, you really want to get it right. If you want to ask more general questions about intelligent motor behavior, you need to account for the salient features that you care about. You need, for example, your fingers to be with some friction, but also slippage can occur, or maybe slippage cannot occur, or maybe there's slack in the joint, or maybe there isn't. You need to choose the space in which you are going to be asking these questions, and you need to model a robot that captures those features. And there's also some tuning. You will get going and you will see that things fly out of your hand because the physics simulation needs some tuning. So even if you're not tuning for a specific robot, tuning is still a challenge. Did that answer your question? In the absence of eye contact, I'm trying to follow up and make sure that.
Yeah, sure. Thanks for the answer. It's very detailed.
Thank you. Other questions?
If you'd like to use the raise hand feature as well, you're also welcome to. And then you can turn on your video and unmute yourself and just ask in person.
So you talked a little bit about kind of end-to-end training to attain like intelligent motor behavior versus kind of applying learning on individual components. What do you think is the role of something like emergent intelligence in robotics?
What do you mean by emergent intelligence?
So, for example, like having multiple individual components come together, where individually they're kind of not really what you call intelligent, but some sort of intelligent behavior could arise from them coming together.
So, to the extent that we're talking about co-learning, you have multiple components and you have crafted the representation between them. But now each of these components is allowed to learn and adapt to the idiosyncrasies of its brethren. I think there's power in that. I think co-learning is definitely going to be better than merely choosing a performance metric for every individual component, training every individual component to that performance metric, and then trying to chain them. If you have an overarching performance metric, and you find a way to co-train your components, that's already a big step forward, even if you have crafted the representation at the interface of those components. But I would argue that maybe you're not like you can no longer account for the semantics of those numbers once you allowed the two components at the interface to both adapt to each other. Like you tell them, speak to each other in terms of quaternions, but you no longer know what do these quaternions mean. Like, are these the orientations of the different segments of the system? Once you're training with an overarching performance metric, nothing is pushing them to align with that representation. So there's beauty in co-learning, but you can no longer pluck one component out and port it to some other thing. So I would be a proponent of that thing, but I would call it more end-to-end training, and it will come with the compromise of less transferability and less interpretability of the data that's exchanged at the interfaces.
Sure, thank you.
What do you think about pushing the end-to-end learning to also include the physical robot?
So,
as in, like, well, like it can be physical robot in simulation, as in not just the agent to control it, but the design of the robot itself to be learned.
So I heard I need to apply some interpretation. I can come up with different interpretations. One thing that I think you may mention is the opportunity for co-design, where I am designing both temporal aspects like the policy changes over time and non-temporal aspects like the shape of the robot. I think co-design is super exciting, and I think you absolutely have to start asking these questions in simulation, because there's no way you're going to tweak the robot, train the policy, tweak the robot, tweak the policy, etc. I think it has a lot of potential, but I think we haven't made a lot of headway because it's a hard question to pose. What knobs do you give your learning algorithm? What do you allow to change? How do you penalize it? How do you measure the performance? You will create this abstract and you will tell it to walk efficiently, energetically. Its legs will become longer and longer and longer, because longer legs are more efficient in terms of the articulation dynamics. But in the real robot, obviously this is silly, because the leg is going to get heavier and the leg will be more either heavier or more prone to breaking. So are you going to start modeling the finite element simulation of the long segment and allow it to bend and measure when it breaks and stuff like that? Like, there's it's really hard to ask that question. But I think it is also really important. I think this is a wonderful research question. How do we ask that question? And how do we make headway in that scientific conversation about co-design?
Perfect. Any other questions from anybody? Don't be afraid to just unmute yourself, honestly.
Can we ever eliminate craft? Because we've gone from using craft to do the representation to using craft to define, the sensory input and the motor output representations, to do crafting reward functions, crafting hyperparameter strategies. So is there an end in sight? Will we ever get rid of the craft bit of it?
So first of all, I would claim that this is progress. Like, we are moving into ever more abstract domains of craft, and and I hope that means that the lower level aspects are ever more efficient. That the learned policies are strictly better than anything we could have crafted. Now, at the end of the day, we are a human society with some goals, and a robot that cannot operate with humans and serve human goals is not going to be a relevant tool. And that is an aspect of craft. Like when I craft the biases and preferences of my children. And I sometimes get it wrong, and then I will pay when they're teenagers. So I maybe the limit after we pop out of the chain of craft, we will hit negotiation. The robot will be smart enough to ask, what do you mean? What is your preference? I can see doing it quick and dirty or slow and steady. What are the budget implications? Like the true intelligent robot will negotiate. But we will never, like, there is no optimal solution because our performance metrics are at that high level no longer well defined.
Good answer. Thank you.
Any more questions from the audience?
So maybe I have one more. So you said there is always a trade-off between accuracy, speed, and stability. But when we look at physics engines, there are still some preferences for this engine, right, over the other, especially if you're doing contact, for example. Why is that?
Not sure I understand the question. Different physics engines hit different targets in this trade-off. PhysX 3 is going to produce awesome animation of explosions, and Bullet, the developer of Bullet, won an Academy Award because that simulation is so useful for making visual effects for movies.
Okay.
But you can't get your robot arm in space right if you're going to use if you're falling at that place in the trade-off map, and you have to aim somewhere else, and you have to use a different algorithm. But I'm not sure I answered your question.
Yeah, I think that was more or less, my question.
Okay.
Yeah.
Any other questions?
If not, if anybody has any more questions, feel free to ask them or raise your hand or put them in the chat. If not, thank you for that presentation, Tom. That was really amazing. Gave us a lot of deep insight into the field itself. So thank you. Thank you for that. Well, we'll obviously, I assume that everybody is already part of the mailing list since this is where we mainly publicized it. But if you're not, please try and join. And Tom, thank you for joining us tonight.
My pleasure. I'm going to stick around for a few more minutes if someone wants to ask questions in like in the lecture room and most people leave and someone wants to stay behind. I'm going to stay for another few minutes if you want to deviate to weirder topics. Otherwise, thanks for having me, and I hope to see you in person one day.
Yeah, thanks so much, Tom.
Thank you.
So, organizers, how did this feel compared to other talks you had recently?
I think it went really well, honestly. I mean, I think it's a little bit of different format. Normally for talks we have like a little bit, it's a little bit less, I guess, goal oriented. It's a little bit more free form. This one was a little bit more structured because there's also these slides and you also knew what topic you wanted to talk about. But I honestly think it would went really well.
You guys scared me by saying that it's going to be hard to get people to ask questions. So I tried to come up with a narrative arc that would be compelling and worth people's time.
Yeah, it definitely really helped. Obviously there are, Ben's, okay, definitely really helped. Obviously there, I think a lot of this is a little bit more difficult because like we don't have that much experience in the field, but your like explanations definitely really helped to kind of clarify that as well. Ben, you've rejoined, so I assume you have something to ask.
No, I just asked the research project people to stay in the call.
Oh, okay.
All right. So if you guys are going to use the room for your own purpose, I'm going to go have dinner.
No, I think
Yeah, no problem.